my postdoc, Larissa Richards, at the University of Leeds. I should say, as usual with work in progress, the results are still being finalized, but hopefully it should at least give an impression of the direction in which we're thinking about things. So I'll start with just discussing the motivation behind the work we've been doing. So it comes from experiments such as are shown in these slides. So what's going on in these slides? Well, on the left-hand slide, we've got a bacteria growing in a petri dish, and it's growing under very optimal conditions. So it has enough nutrients, and under these reasonably optimal conditions, what we see is that the bacterial cluster tends to just sort of move out equally in all directions and fill all the space available at a fairly constant rate. And so you end up with the growth being disc-like. I'm not sure how well you can see it, but you can sort of see the different epochs of growth in this picture. And once it gets to this side, you start to get a few imperfections, but essentially the cluster is just growing out in an isotropic way. The picture on the right-hand side is the same bacteria, but this time it's in an environment where it's been deprived of nutrients. And so this time it can no longer afford to just spread out, filling all the available space. And so it starts to make choices and sort of pick certain directions which are more preferential and other areas where it chooses not to explore. And in fact, this is even more prominent in the second set of slides, where again it's the same experimental setup, except in both cases, the agar on which the bacteria is growing is much harder, and so it's less beneficial to grow on. And so you can still see in the presence of many nutrients, it still almost fills all the available space, and it almost grows out at sort of constant speed in all directions. However, when we deprive it of nutrients, then you can really see very clearly that it's starting to have to pick certain directions and just explore those directions. And for people who are familiar with the model diffusion-limited aggregation, or DLA, you might notice that the shape of the cluster that we get starts to look like a DLA cluster. So the question that I'm sort of interested in is, in all cases, the experimental setup was completely isotropic. The nutrients were evenly spread across the dish, even if in some cases there were fewer than others, and yet the model has somehow spontaneously become anisotropic. It's spontaneously chosen directions. And so this is the question that I'm sort of interested in, is what is the mechanism that causes this breakdown of isotropy, that causes a spontaneous choice of preferential directions? Okay, so how can we study these kind of questions? Well, to start off with, we need a mathematical model for random growth. And some of the earlier models for random growth tended to study them on a lattice. So take for instance, the square lattice. You would take say a bacterial cell at the origin, and then with certain properties it would reproduce into the neighboring cells, and you could grow a cluster in this way by at each point choosing one of the boundary cells and adding it to your cluster. Now, I would argue that this isn't the best model in which to study this question of breaking down of isotropy, because before we've even started, we've broken down isotropy, because we're on a lattice, say a square lattice. We've already got two preferential directions before the model even starts to grow, and so there's no reason on a square lattice that you would expect to get round clusters. And so trying to understand why you might get clusters that break the symmetry isn't so it's not so clear studying that on a lattice. So rather what we want is a framework in which we can study random growth, which is fundamentally isotropic. And then if at any point we're able to show that this anisotropy breaks down, it has to be coming from within the model. It's not something external to the model that's caused that to happen. Okay, so how are we going to do this? So throughout this talk, I'm going to restrict to being in 2 dimensions. And the advantage of being in 2 dimensions is that we can view our clusters as compact subsets of the complex plane. And that allows us to use the Riemann mapping theorem to say that we can uniquely identify our cluster with a mapping. And so first of all, I'll start by showing how we can represent a single particle, and then I'll show how we can construct an algorithm for constructing growing sets of clusters. So just a bit of notation. So let D naught be the exterior unit disk in the complex plane, and P denotes a particle. Then, as I said, by the Riemann mapping theorem, the cluster with a particle attached to it is a compact set. Its exterior in the units, therefore there exists a mapping from the exterior of the unit circle to the exterior of the unit circle without that particle that fixes infinity, in the sense that if you look at the Laurent expansion of the conformal mapping at infinity, it's a real number times it. So there's no rotation caused by any complex components. And in fact, you can show that this real factor is strictly greater than 1 to represent that the disk with the particle is strictly bigger than just the unit disk. And this parameter C tells you something about the size of the particle that you've discussed. And this will be a parameter that we'll see throughout our talk. And we call C the capacity of the particle, and it will allow it to control the different sizes. So here's a simple example. In this picture, I've taken my particle to just be a slit in the exterior unit disk. And so I have a unique mapping that maps from the exterior of this disk to the exterior of this disk minus this slit. The slit is kind of convenient because, in fact, in that case, you can write down this map explicitly, and this is useful for doing simulations. And so in any of the simulations that I show, I'll be using the slit particle. However, as I'll discuss in a few slides' time, other particle shapes fit completely within the framework, and our theorems hold in quite wide generality. Okay. Oh, so in fact, this is the slide that I wanted about the particles. So, as I said, this capacity parameter is very useful because it allows us to control the size of the particle, and we're going to need a family of particles that correspond to all the different sizes from 0 to infinity. And we want to choose our family to satisfy certain properties. The first one is that the smaller particles with smaller capacity are enclosed within particles of larger capacity. And the second criteria I've written by this display line is that the radius of the particle seen from the position 1 is bounded by some constant times the distance of the height of the particle. And essentially what the second condition means is it just it forces particles to concentrate near the point 1, but it also rules out particles being too flat. And so here are some families of particles that we're allowed to use. So the slit one I've already talked about. You can see small slits are contained in larger slits, and the radial distance from 1 is the size of the slit, and in fact, in that case, it's exactly equal to the distance from 1. So capital lambda is equal to 1 in this case. The second particle family, these are this is a sort of disk centered on the boundary of the disk of smaller radius. And again, if you imagine concentric circles all centered at 1, you have this inclusivity property, and again, you have the concentration around 1, and the fact that this isn't too flat. And then the third example is really what most people would like to think about when you think about attaching a particle to a cluster, which is just attaching a tangential disk. And again, you can see how if you have tangential disks of increasing radii, they're all contained, smaller ones are contained within bigger ones. And again, the radial size from 1 is the same in this case also as the height. So capital lambda is equal to 1 in that case. So these are all types of particles that you can think of, but really any class of shapes you can think that satisfy these conditions will hold. Our results will hold for these. Okay, so we know how to. So I should just say, if anyone has any questions, feel free to ask. But I can't see the chat, so if anyone puts anything in the chat, then if someone in the room could read it out to me, that would be helpful. Okay, so now we know how to construct a sort of seed I guess this corresponds to the initial seed of bacteria with a single new bacterium attached to it. How do we increase this process and get particle clusters with many particles on them? So I've written the algorithm on this slide, but don't worry if it's a little hard to parse. I'll show you a picture on the next slide, which will make things clearer. But supposing that we want to attach a whole sequence, we want to grow particles sequentially one by one. So we need to start off with a sequence of particles that we're going to attach. And for each particle, we just need to know the capacity and the attachment angle. The capacity is going to correspond to a particular particle of that capacity here. And we know from the previous slide that we have a unique mapping that attaches a particle at position 1. What we're going to also want to do is we also want to allow different attachment angles. And so once we have this mapping for attaching a particle at position 1, we can just conjugate it by rotation to get a mapping putting the particle at any position. And so with a fixed capacity and a fixed angle theta n, we can construct a map Fn that corresponds exactly to this Cn. In other words, that takes the exterior unit disk to the exterior unit disk without a particle of capacity Cn attached at angle theta n. Okay, so let's start our process off. So we start off with our base mapping corresponding to the empty cluster, just being the identity map, and that takes the exterior unit disk to itself. So that's we just have our seed set of particles and nothing attached to it. And then supposing we have the map corresponding to n-1 particles being attached, from this we construct a map which is going to correspond to n particles by precomposing with the Fnth map that we got from above. Why is this a sensible thing to do? Well, what we can show is we can first of all show that, I mean, these are clearly conformal mappings because they're compositions of conformal mappings, that from the exterior unit disk to a compact cluster, and this is the key observation, is that the cluster corresponding to the n-1 map is strictly contained within the cluster corresponding to the nth map. And so that means that we have strictly growing sets. And so this gives us a mechanism for describing a growing object in space. Okay, so let me explain this conclusion that Kn-1 is a subset of Kn. So I'll do this with a picture. So here's our exterior unit disk. And this is our mapping phi n-1, which takes us to the exterior unit disk without the n-1 particles. And for this one, I've used slit shapes to correspond to that. So these n-1 sort of curves correspond to n-1 particles being attached. Okay, what happens if we precompose this mapping phi n-1 with the Fn particle map? Well, the Fn particle map takes the exterior of the unit disk to the exterior of the unit disk minus a slit of capacity Cn attached at angle theta n. So what happens if you then compose this with phi n-1? What do you get at the composition of the two? Well, we already know that the exterior unit disk under phi n-1 goes to the exterior of the black cluster. So we just need to remove from the image the image of the blue line, and the blue line is in the exterior unit disk, so it's going to give us something outside the existing cluster, but it's attached, and so we end up with something attached. And so interpreting the image of this blue slit as a particle, we had n-1 black particles. We've now got the n-1 black particles plus one blue particle. And so in the right-hand picture, we have a cluster with what we consider to be n particles. And so that means that we have the property that we wanted. And so taking this definition as phi n-1 composed with Fn, you can sort of expand this out, and you can see that the nth particle map is basically the composition of the nth cluster map is the composition of particle maps corresponding to the first n particles, but composed in a sort of left to right order, which is the sort of opposite of what you might expect if you're sort of used to working with, say, things like marker processors or things like that. You expect to have things the other way around, and it's this reverse composition that is one of the things that makes these models a little bit tricky to work with. Okay, so before I move on, any questions about the construction of the model itself? Okay, so one thing to sort of ask ourselves before we move on is what did we need to know in order, what inputs did we need to be able to construct a cluster? And the input we needed a sequence of capacities and a sequence of angles. So if you give me any sequence of capacities and any sequence of angles, I can then construct these mappings Fn, and then I can just compose them, and I can give you back the cluster that results from that choice. And in fact, you don't even need to give me a deterministic sequence of capacities and a deterministic sequence of angles. You just need to give me a rule for choosing a sequence of capacities and a sequence of angles. So as long as you give me a rule that's that sort of makes sense, that I can perform, I can use that rule to construct the capacities and angles, and then I can grow you the cluster. And so, in other words, by varying these sequences, phi and the theta n, we can really describe a very, very wide class of growth models. So the question we might want to ask ourselves is, can we choose ways of selecting the theta n and cn that correspond to the physical models that we want to look at? So first of all, let's think about the biological growth that started with the picture I first showed you. So what happens in that case? Well, we need, supposing we have a cluster with n particles. In order to grow the next one, we need to decide where is the next particle going to attach, and how big do we need to choose our capacity parameter. So the first question to ask ourselves is, where is it going to attach? Well, because it represents biological growth, we can kind of assume that we want to pick an angle uniformly at random on the cluster boundary. And we want to pick it proportional to the arc length. So if you've got parts of the cluster that have a very long arc length, there's many more underlying sort of microparticles under there that could be reproducing, so that should have a higher probability. And if there's something that has very, very short arc length, then there's sort of very few particles. There are very few cells there, so that should have lower probability. So we want to pick our angle theta n in such a way that the probability of picking theta n lying in a particular region is proportional to the arc length of the cluster between these 2 points A and B. And just using arc length computations from calculus, this means that this is the computation for arc length of our cluster between these 2 points, e to the IA and e to the IB. And so you can see that we get a distortion. So I put down a slit of a certain the not being a straight doesn't matter.
Amanda, can you hear me? Milton, ¿você está ouvindo?
Aquí te oímos, te escuchamos, Inés.
So,
No, Amanda.
Amanda, we're having trouble with the audio.
Yeah.
I think it's you, though.
Yeah, so here we can also, we're also having trouble listening to Amanda.
Can you hear us, Amanda? No?
So, Amanda, we lost your audio for a while.
I think connection. No tengo el...
No hay por el
No, dice que no lo puede ver. No lo puede ver. Pablo, prende ese radio de paso. O alguien bajo el otro. Su nombre.
E ça fait que, là,
Hello, can you hear me?
We can hear you, Ines, but not Amanda. So I think it's Amanda's having trouble.
Hello, can you hear me now?
Yeah,
Okay, sorry, my internet's gone unstable, but I'm using a hotspot now, so hopefully that will work. At what point did I lose you?
I think you have to share your screen again. We're not seeing the slides.
Um,
Good.
So yeah, so right before that that slide, we lost you.
so did you see the slide at all?
Yeah, we can see your slide.
No, but did
We have
I
seen.
talk about this?
Yeah, we got that one.
We got this one. Okay,
Yeah.
did you get the justification of the Eden model?
Yes.
Okay, so I think I was just about to justify the particle size. So what I was trying to explain is that in the cluster, what we end up getting, we don't get the original particle that we put down, which was in this picture a straight line of length corresponding to capacity Cn. Instead, we get the image of that line under the mapping phi n minus 1. And that image causes a distortion, which first of all changes the shape. So instead of being a straight line, you can see we get a curve, which are actually sort of geodesics towards infinity in the Riemann sphere. But also potentially you get a length distortion. And this is in some sense unphysical. So if we want to be studying physical models, we would really like to have particles that are roughly all the same size. And the curve distortions we can't avoid, but in some sense, if you just think you're very, very small particles, which is what we're going to do in the limit, that doesn't matter. But the length, we really do want to have all our particles of the same length. And so again, the way we can compensate for this is we can work out what distortion we're going to get in the image, and then we can choose our capacity in such a way that it's a different size in such a way that when it gets distorted, it becomes the same size. And so again, if you can think, if we had a slit of a particular length, what length is it going to be in the image? Well, you just need to do the arc length computation again of what happens to this curve under this mapping, and that involves sort of integrating the derivative over the length of this slit. Again, if we suppose that our slit is very, very small, then that's approximately just the value of the derivative at the attachment point multiplied by the length of the slit. And so that tells you that if we want to have in the image our particle the right size, we need to pre-divide the capacity by the derivative at the slit. And so this is, so to choose particles that in our image will all be the same size, we take our nth capacity to be the just some base capacity that we pre-choose, that be a parameter of the model, divided by the derivative at the attachment point. And then if you think about what happens to a particle of this size, when you get map it out, it gets multiplied by the derivative. Well, so the slit gets the slit is roughly, so one thing I didn't say, the size of the slit corresponds to roughly the square root of the capacity. And so in our pre-image, the slice is going to be something that's divided by the derivative, and then when we multiply by the derivative in the arc length computation, these two cancel, and you just end up with all of your particles as roughly the same size. Okay, so in some sense, these choices don't matter too much, the precise details of them. The important thing, rather, is that we have a way of choosing a rule for constructing our angles theta and our capacity Cn that corresponds to a physical model that we're interested in. The second model that we might be interested in, as I said, is this diffusion-limited aggregation model that I alluded to in the introduction. Now, what happens in that case is, how does DLA grow? Well, you have a cluster, and the next particle is attached according to the hitting distribution of a Brownian motion started from infinity. And so we need to choose an angle theta n within AB is such that the inverse mapping, it should be chosen in such a way that a Brownian motion starting at infinity lands between the image of A and B in the image picture. And so pulling that back, that means that the pre-image of the hitting position of the Brownian motion must be in this length AB. So this is the choice that we need to make for DLA. And then something really nice happens, which is we remember that phi is a conformal mapping. So that means that phi inverse is also conformal mapping. And then we remember that Brownian motion is conformally invariant. And that means that the hitting distribution, the trace of a Brownian motion under a conformal mapping is also itself a Brownian motion. And so this quantity phi n-1 inverse of BT is itself a Brownian motion. And so we want to know what's the hitting distribution of a Brownian motion on the unit circle when started from infinity. And now we've started from infinity, the unit circle is completely symmetric as seen from infinity. And so that's just proportional to the length between A and B. And so in this case, we're picking theta n to be uniform on the unit circle. And exactly the same argument before says that we choose capacities as before to ensure our particles are roughly the same size. So we can also construct DLA. And then we can sort of think, well, what we wanted to see was how a model might break down between biological growth and DLA, how the isotropic behavior might break down. And so it makes sense to see whether we can naturally interpolate between the Eden model and DLA. And one way that we can do it is you can sort of see, in this case, the angle was chosen with density given by the derivative. And in the second case, the density was given by the uniform, but you can sort of think about that as actually being the derivative raised to the power of 0. And so that gives us a way of interpolating between these two, is we can sort of introduce a parameter corresponding to a power on the derivative. And as that parameter moves between 0 and 1, we interpolate between the Eden model and DLA. And so that motivates a sort of wider class of models, which I call aggregate Loeffner evolution. And so what is the aggregate Loeffner evolution model? Well, it's a 3-parameter model, got parameters alpha, eta, and sigma. It falls exactly into this class of conformal growth models that I've talked about, which means I just need to tell you what my rule is for picking my attachment angles and my capacities. And I've given them by these two formulas written at the top of the screen. So first of all, let's just ignore sigma and just think about the other parameters. So if you ignore sigma, just say set sigma equal to 0 in your mind, then taking eta to be minus 1 gives us, and alpha to be equal to 2 gives us the Eden model from the previous slide. So I've marked that down on the picture. Picking eta to be 0 and alpha to be 2 gives me DLA, again, that I've marked with a black dot on this picture. So this picture is a map of eta against alpha. And the interpolation that I talked about between Eden and DLA is again on this blue line that I've written here. Okay, so certainly a subset of this class are these physical models that we're interested in. But why have I moved from a 1-parameter family, which to a 2-parameter, well, to a 3-parameter family, but even before sigma gets involved, into a 2-parameter family? Well, the reason is that if you want to grow a model in which growth is concentrated in a particular part of the cluster, you have 2 ways of doing that. You can either choose your attachment angle density in such a way that you're very likely to pick angles corresponding to that region of the cluster, or you can pick your capacity sizes in such a way that if you land in that region of the cluster, you have much bigger particles. And so in some sense, you can trade off attachment density against particle size. And it turns out that the on average, the way to trade them off is if you look at the product of these two, the attachment density times the capacity formula. If the product of those matches, it's only the product of those that determines the average, the final limiting behavior of the cluster. And so, because these two both have the same shape, if you look at the product of them, you end up with the derivative of the power of alpha plus eta. And so what I would argue is, in the picture I've drawn these diagonal lines corresponding to alpha plus eta taking constant values, is I argue that heuristically, any model with parameters taken along a single diagonal line should have the same kind of behavior. So instead of studying the Eden model by taking alpha equals 2 and eta equals -1, I could take, for instance, eta equals 0 and alpha equals 1, or I could take, for instance, alpha equals 0 and eta equals 1. And all of these, in some sense, should correspond to biological growth. And similarly with DLA, I should be able to choose parameters anywhere along these diagonal lines. How is that helpful? Well, it depends what you want to be doing. So if you want to be doing computer simulations, sampling from this theta n distribution when eta is non-zero is very slow and very difficult, because this phi n prime map can be quite quite spiky. So you need to sort of be able to compute it at lots of different values, and it can be very, very hard to get good simulations of taken from this distribution. However, if eta is equal to 0, you're just simulating a uniform random variable. That's very easy. And then we just need to compute this phi prime map at a single value corresponding to that attachment point, and so that can be quite quick. So if you want to do computer simulations, you really want to choose eta equals 0, and so you want to be looking at models on this red line, and this red line actually has a name. These are sort of Hastings Levitov family of models, which were proposed in '98 by Hastings and Levitov. On the other hand, if we're mathematicians, then having the capacity constantly changing is very difficult, because we don't know what scale our particles are, and so we don't know how to look for scaling limits, because sometimes we can be attaching very small particles with very small capacities, sometimes very large ones, and the model's a bit all over the place. So as mathematicians, it's a lot more convenient to put alpha equals 0 and have everything on eta. And so for this green line, this makes our life much easier as mathematicians. And so that's was the reason to that we sort of proposed this wider family of models, was in order to take to find a place where we could actually do mathematics more easily. And then the idea was, if we could prove some theorems on the green line, then we might be able to push out our methodology to get things working across the full length of the diagonals, and in particular onto the blue line, which is where the physics really lies, which is what we're interested in. Okay, so that's where this family came from. What about this parameter sigma that I haven't mentioned just yet? Well, there's many difficulties with these models, but one of them is that the mapping phi n prime is very badly behaved. So phi is a conformal mapping on the exterior unit disk. That's fine, and you can extend it by continuity to the unit disk itself. However, the derivative is only well defined in the exterior unit disk, and if you try and extend it by continuity to the unit disk, you find it can take the values 0 and infinity. And so for certain values of eta, you might even find that this density doesn't normalize. And so when I defined say theta and was taken according to this distribution, if sigma is equal to 0, that measure might not even exist. And so I need to have some kind of regularization in order to define the measure. And so this was the solution, was to basically, instead of evaluating the derivative on the boundary, evaluate the derivative a small distance away from the boundary, given by a parameter sigma, construct your model, and then take the limit as sigma goes to 0, and try and recover what we really wanted. In theory, that all sounds fine. The problem is the models are really sensitive to the rate at which you take sigma to 0. So you really have to tune sigma carefully in order to see what you want. And physicists argue that taking sigma like root c is the natural way to do it. Okay, so having sort of constructed the model, what is it that we really want to ask ourselves? Well, the big open problem is, does this model exhibit a phase transition from disks to non-disks along this line alpha plus eta equals 1? And this is sort of a broad choice of the regularization parameters. So I don't want to sort of answer this question where I've tuned the regularization parameters so carefully that that it only works because of that tuning. I want a more robust mechanism for a phase transition. And as I said, this fits in with these long-standing conjectures that Hastings Levitov model. So that's this red line has a phase transition at 1, and dielectric breakdown is this blue line has a phase transition at eta equals -1. Or sorry, at eta equals sorry. It's eta equals 0, but yeah, dielectric breakdown. This should have been, so this should be eta plus 1. There's a shift in the notation from what's used in the physics literature to what I've put there. Sorry, so there's a small typo there. Okay, so before I carry on, let's just look at a few simulations of this ALE model, just to see that it looks like that actually the simulations indicate a presence of a phase transition. So all of these are simulated for the mathematical values. So all my simulations are for the green line. As I said, it's difficult to simulate along this green line. The red one's much easier, but I just wanted to do simulations here just to really see that we hadn't simplified to a point of not having a phase transition. But these simulations really took a very long time to do. So I've only got 8,000 particles, which is pretty small. So this is the sort of Hastings Levitov 0, model corresponding to both of these parameters being 0. And this is in some sense the simplest model to study because in that case you just have IID rotations of maps with the same capacity. So and that there you can see the different colors correspond to different epochs of arrival. So the red particles arrive first and the pink particles arrive quite late. But you can see that it really does seem that we're getting a disk scaling limit here. So it's just growing in an isotropic way as you might expect. And in fact, this is a theorem. So actually, I proved this in my PhD in 2012. Okay, what about if we change the eta parameter to now 0.5? Again, it's still looking fairly disk-like. Now we go to 1. So this is the one corresponding to the Eden model, to biological growth. And it's still looking kind of round, but with some sort of slightly bigger fluctuations starting to form. 1.5 now, it really is, it'd be hard to still think that this is a circle anymore. Some of these fjords are getting quite big, so it really does seem to be picking some preferential directions, and there's simply parts of the cluster that it doesn't want to grow into. And then this is parameter 2, so this corresponds to DLA, and now you can see really it's made very clear choices of preferential directions. And I think I think this one you might think, oh, maybe if I run it a bit longer, it might converge to a disk. I think in this case, it would be quite hard to. I mean, we can't prove it doesn't converge to a disk, but it would be quite surprising if this cluster did suddenly recover itself and stabilize. And then I also did a cluster just with eta very, very large at 5, and you can see now it really has picked just one preferential direction, and it's just running with it. So in terms of a phase transition, I think it's reasonably clear that even in this mathematically simplified model, we really do have a transition from those sort of disk interface, non-disk, very much sort of one-dimensional cluster. Okay, so what are the results that we've been able to prove? So the first set of results that I've got are due to myself in collaboration with James Norris and Norris and Silvestri. And these results are in 2 papers from 22 and 2024. And essentially we followed the program that I've described. Was in 2022 we proved the result for the models on the green line, which I said was the mathematically more simpler one. And then in 2024 we were able to push down the diagonal lines and actually show that our results held across the whole parameter of families, the ALE families. And essentially these are results in the disk regime. So these show us when we when we're in this case before the phase transition, where we get disk-like limits. And so we show that for all families in which alpha plus eta is less than or equal to 1, so we're below the Eden model, that the particle map approximately behaves like a growing disk map. And furthermore, we're able to look at the fluctuations around that disk, and we show that the correct way to rescale in order for the fluctuations that the fluctuations are of scale root c, so c was the capacity parameter, and if you rescale by that, then we got that the fluctuations could be given by an SPDE of this explicit form. And the key observation to make here is this 1/1 plus alpha t factor is just a time change. So that doesn't change anything about the solution to this SPD, just changes the time scale. So if you ignore this factor, then really the fluctuations only depend on the value of alpha plus eta. And that's what I sort of said with the heuristic at the start, was that we somehow believed heuristically that all models along these diagonal lines when alpha plus eta are constant should behave in the same way. And this shows us that certainly in the even at the level of fluctuations, that really it is only the values of alpha plus eta that matter. If you're not quite sure how to interpret an SPDE like this, well, one of these ways to think about it is each of these mappings, FTZ, are conformal mappings in the exterior unit disk. So we can write down a Laurent series for them in this form, and we can by equating both sides of this equation, you can deduce stochastic differential equations for the Laurent coefficients, and they are given by this, and these are just Ornstein-Uhlenbeck equations. And so we can basically our limiting fluctuation process is just a conformal mapping whose Laurent coefficients are given by Ornstein-Uhlenbeck processes, and in particular that means that the distribution of the coefficients is a Gaussian with these parameters. What's interesting about this value is that you can see that we had this assumption that alpha plus eta was less than or equal to 1. What happens if alpha plus eta is bigger than 1? Well, this doesn't make sense anymore. These coefficients start to explode, right? So if alpha plus eta is less than 1, these coefficients are all bounded. If alpha plus eta is bigger than 1, then these coefficients start to explode as n gets large, and that means that this field doesn't actually have a convergent value when mod z is unless mod z is taken sufficiently large as well. And so what does that tell us? So if alpha plus eta is strictly bigger than 1, we would need to take mod z strictly bigger than a particular value for FTZ to converge. And so that means that we unfortunately haven't been able to prove that the existence of a phase transition was what we really wanted. But what we have been able to show is that if there is a phase transition, if there is no phase transition and you get disk limits even when alpha plus eta is bigger than 1, that the fluctuation process has to change, because our fluctuation process doesn't make any sense when alpha plus eta is bigger than 1. And so this is the sort of beginnings of a phase transition. And I think this is one of the first results that really picked out that something special is happening at alpha plus eta equals 1, that the behavior of the processes can't stay the same across these values, and that in some sense something is starting to happen. So we haven't been able to show that the isotropic behavior breaks down, but we've definitely shown that the fluctuation process around a disk limit cannot persist into this alpha plus eta bigger than 1 range. A couple of other observations. So the one is that this mapping is determined just by its Laurent coefficients. Well, that means that on the cluster boundary, it's a Fourier series, and so it determines Fourier coefficients that give you a boundary process. And so, in fact, if we know the boundary process, we know the Fourier coefficients of this, we can reconstruct the Laurent process. And so our mapping really is just determined by a boundary process. And so you can ask about what are the properties of this boundary process. And there's a few interesting results. So the first is that in the HL0 case, when alpha and eta are 0, these boundary fluctuations are exactly the same as internal diffusion-limited aggregation. And the second thing that we can do is we can let t go to infinity on our boundary process and ask whether we get some sort of stationary limit. And in all cases, you can show that there is a stationary limit, and it's a Gauss that it converges to a Gaussian field. When alpha plus eta is 0, it's known as the augmented Gaussian free field. Provided alpha plus eta is strictly less than 1, it's a log correlated Gaussian field. And when alpha plus eta is equal to 1, it's complex white noise. And so again, you can start to see from these results that something special is happening at 1. Some behavior is changing across the process. Okay, so can I just ask, do I have any time left? I wasn't sure, is it a 50-minute talk or a...
So you still have like a 5 minutes, maybe in according to our clock. I don't know.
Okay.
So-
Okay, yeah, if I have 5 minutes left, I can talk a little bit about the local limits. So far, I just didn't want to start if I had no time at all. But yeah, so since these results I talked about with James, Norris, and Silvestri capture the global limits of the whole process as holomorphic maps on the exterior unit disk. And this boundary process identifies the fluctuations where we take our process and we look at the fluctuation process at a fixed distance away from the boundary for some fixed value R. We let C go to 0, our capacity go to 0, and analyze this process, and then finally to get the boundary process, we let the radius come down to 1. But you could ask the question, well, what happens if instead of fixing a radius, taking a scaling limit, and then letting that radius go to 0, what happens if you let R go to 1 at the same time as C goes to 0? Is there a natural speed at which you can do this that results in a non-trivial process on the line? And you would definitely have to scale this value, because, for instance, if we took R equal to 1 immediately, what we're getting is we're getting the boundary of the cluster, and the boundary of the cluster traces out the whole shape of the cluster all the way around it, and so it's going to revisit the unit disk and the exterior of the cluster on every branch. And so very clearly, if you took R actually equal to 1 on this fluctuation process pre-scaling, it's not going to have a scaling limit. It's going to sort of be constantly it's going to be extremely rough, because it's going to be going from the radius into the center of the disk and out again infinitely many times as we go. So we would have to, if we want to look at R becoming close to 1, we do need to tune the rate at which R goes to 1 to get something non-trivial. And in order to explore this local behavior and how to do it, for simplicity, I'll just restrict to the alpha equals 0 case, and we anticipate a phase transition in local limits at eta equals 1. So what are the results that we have? So this is the work in progress with Larissa. So for this, we take a point Z at a distance e to the b from the unit disk, and we want to look at b tending to 0 simultaneously to c tending to 0. And so here's our first result, is provided that sigma doesn't tend to 0 faster than c to the 1/4, and b doesn't tend to 0 faster than c to the 1/2, the fluctuation process scales like root c log 1 over b, and it converges to a complex Gaussian random variable. So this is a complex number. It's got real and imaginary parts, and so the limit is a real and imaginary Gaussian who are the real imaginary parts are independent and each have this variance. And so you can see we had to sort of rescale by a slightly different amount in the local case. In the global case, we just scaled by root c. In the local case, we also have a log 1 of b correction. And we can also look at the 2-point correlation function. And it turns out that this depends on the ratio of the log of the distance between our two angles. And so if we take 2 points, an angular distance A apart, but each at radial distance B, then, well, we know individually each of them converge to these complex Gaussians. But what is the covariance structure between the two? Well, the real parts have correlation given by these two. The imaginary parts have the same correlation, and the real and imaginary parts are uncorrelated across each other. And you can sort of see gamma can take values between 0 and infinity. And when it takes the value 0, then obviously that means that these two are just completely independent. So that means that if 2 points are sufficiently far apart from each other, that they're independent. And if we get above 1, then these are perfectly correlated. Okay, so that's the eta less than 1 case. What about the eta equals 1 case? Well, this, it won't surprise you, that starts to again behave very, very differently. And in fact, we find that we have 2 subcases, which we really hadn't expected when we started this program. That if we look at a local limit where the radial distance tends to 0, strictly slower than root sigma, then we get then we have to rescale by c divided by that radial distance, which already, so you can see the scaling factor is different to the log scaling that we did before. But even more surprisingly is if b tends to 0 faster than root sigma, then the scaling factor of the fluctuation actually doesn't depend on b at all. It only depends on sigma. And so we really didn't expect to see these 2 different kinds of behavior depending on how fast how close we scaled in our local fluctuations. But once again, we can look at the 2-point correlation functions, and now again something looks different to before, because before we had that the real and imaginary parts were uncorrelated. Now we pick up that we do get correlations between the real and imaginary parts. Although again, if gamma, which is this limit between A and B. So remember, before it depended on the log of A divided by the log of B, whether the points were uncorrelated or not. Now it just depends on the ratio of A and B. So again, they decorrelate at a different rate. So if they decorrelate fast enough, you do get the real imaginary parts are uncorrelated, but you can also have a regime in which they stay correlated. And so this was the case where b over root sigma was equal to infinity. And then the second case, we also have 2-point correlation functions, which again allow interactions between the real and imaginary parts. Okay, so I slightly raced through those results due to shortage of time, but I'll just end with a little bit of, as I said, this is a work in progress. So what do we still need to do? So I've talked about point-wise convergence of the local fluctuations and 2-point correlations. But there's this natural question of, can you prove convergence of local fluctuations as a process? I slightly glossed over these conditions on sigma, but if you remember, I have these sort of conditions here saying that sigma can't tend to 0 too fast. So can we either relax these constraints or show that those constraints are there for a reason, that there is actually a phase transition in sigma as well as a phase transition in eta. We've done the scaling limits for the actual process. You can also ask the same question for the local derivative, and our methodology looks like it should work quite nicely there as well. And then a couple of harder questions. So we expect KPZ universality in the eta equals 1 case if sigma tends to 0 at the appropriate rate. So can we say anything with that? And very, very hard. Can we say anything at all when eta is strictly bigger than 1 and get things that aren't at disk limits at all? Okay, so that's sort of all I wanted to say, and I'll just end with some references.
Okay, thank you very much. Questions?
So I have a question. So at the beginning, you show us some pictures, no? That of this. And what I didn't I didn't understand that. So these different pictures, which regions of parameters on your phase diagram more or less correspond?
Yeah, so we think this one where the bacteria can grow in perfect conditions is going to correspond to the parameter 1, the Eden model, which, going to my diagram, is this diagonal line here that goes through the values 0, 1, and 1, 0. And this one where it's very, very stressed and can only grow where so you can sort of think about it as there's very few nutrients in the agar. So you can almost think of a case of some nutrients are diffusing in slowly from outside, and only where a nutrient hits the cluster is it able to grow. So that corresponds to the diffusion limited aggregation, which is this one here. And in my parameter, that was choosing theta n to be uniform. So the hitting diffusion of Brownian motion. And then these in between ones where it's sort of it's a little bit stressed, but it's still able to grow. We sort of anticipate that somehow these should be values in this interpolation region. And then if we look at our simulations, so this should correspond to Eden. So this is growing in very comfortable environment. This one is starting to get a little bit stressed, so starting to make some choices, but largely filling the area. And then this is getting very stressed and having to pick very, very particular directions.
Yeah. So related to that, Tom, you were saying that when you go to parameter equal to 1, so is where you get the KPC. You expect KPC fluctuations, right?
That's right. So that's this picture here is where we expect to see KPZ. Yeah.
Yeah. So at least for me, it's a little bit counterintuitive that when the model is smoother, then you get more complicated fluctuations in a sense.
Yeah. So it's in fact this is a sort of interface smoothness, right? So when we take values smaller than 1, we get very, very smooth boundary. So these two values are smaller. So in my picture, just to go back to here, we're in this region down here. We're even below the Eden model. We've got even smaller parameters. And so here we're getting very, very smooth results. And this is where we're getting our Gaussian fluctuations that I talked about in the result. This is the sort of interface where if you look far enough away from the boundary at the fluctuations of a sort of level line, that's a little bit away. Again, it's smoothed out and we get Gaussian fluctuations. And where you expect KPZ is if we choose our envelope. Like I said, you have to make a choice in the envelope, because if we take it 0, then really you're tracing out the whole cluster, and you haven't even got a scaling limit, right? So you have to pick some little envelope to look at to even have a disk limit to first order. But if you choose that so that you just start to see the roughness, then that's where we expect a KPZ. Now in this case, you don't even have a disk result, right? So we can't expect to see KPZ in this regime because the fluctuations are macroscopic in this case. So this has to be in a different universality class. So really the only place you can expect to see universality is at the critical point where it's a disk, but only just a disk. And that sort of is consistent with that.
Okay, thank you.
Sorry. Any further questions? Amanda, just I was a bit not clear on this. This conjecture that this bound thing you had where you had the two lines and you expected that the relevant parameter was just eta plus lambda plus alpha. Sorry. This is you proved this or just a conjecture? So
we've proved it in this subcritical regime where we're below the line. And when I say we proved it in the sense that the scaling limits are disks everywhere, right? So it's and below this line. So in some sense, the line disappears if you only look at the scaling limit. but we proved it at the fluctuations, that the fluctuations only depend on the on the intersect on the gradient of this. So I mean on the intersection point of these lines. So I think in some sense that's the best equivalence you could hope for, which is that that we found a scaling property that only depends on that slope. So yeah, so as I said, when you said have we proved it's equivalent, it's a little bit difficult to know what that means when all clusters just give you the same shape. But I think to say that the fluctuations are exactly the same, I think does show that you have universality along these diagonal lines. When we're in the region above that line, as I said, we can prove almost nothing there. So and in some sense that's the place where it's more interesting, because what you would really want is in these cases where you're getting macroscopic random shapes, you would want to know that they have the same characteristics. So the DLA, the true DLA, should sort of in some sense have the same fractal dimension as my version of DLA, corresponding to the green line. So my DLA over here should have certain statistical features in common with this DLA here. So that's really where it starts to become meaningful about what you mean by equivalence is are there statistical properties shared along these things. Down here, the statistical property we have at the fluctuation behavior is exactly the same along diagonal lines. So I guess you can say we sort of partially proved it in the sort of least interesting regime. But yeah, the more interesting regime we just don't know how to touch. Unfortunately, it seems very, very hard to say anything above the Eden model.
Thank you very much. More questions? If not, okay, let's thank Amanda again for a really nice talk. Okay, I guess we'll meet again next week.
Okay, thanks. Bye then. Bye.
Thank you very much.
Bye, Amanda. Thank you very much.
Bye.